we're presenting a self-landing rocket in a simulation. I'm Kristian, Paul, Francesco, you all know us. So we're pretty much going to walk through it. We're going to talk about what the goal of the project was, why we wanted to or cared to do it, kind of a little bit about the system and how we approached it, and then pretty much top it off with our results and how it looked and what still needs to be done in the future. So our goal was to land a small rocket using thrust vectoring by being controlled by reinforcement learning algorithms, so policy. Like SpaceX, but with a smaller rocket. And the motivation for this is really just questioning, can we use a hybrid single-stage rocket to land without a parachute and generally low altitude where it's moving a lot slower, it's hard to keep your balance. So the process, we kind of had the midpoint where we just kind of started looking at the related work. We kind of tried to understand how a rocket works and the specs we were going to be using, and then finally tried to implement a really simple Monte Carlo in one dimension. After that, we kind of worked in thrust vectoring. Francesco, Paul spent a lot of time speeding up the simulator and multi-threading it so we could run a lot faster, and then finally actually land a rocket instead of having to shoot off. So if you're wondering why we didn't use a real rocket, it's because SEDS, the rocket experts on campus, this is them testing their hybrid engine, and it failed like a second in and blew off. So that's why we had to stick to a simulator. And why without a parachute? Because it's fun to land rockets without a parachute. We're going to use it for a senior thesis. It looks really cool. Maybe it would help for landing on planets with smaller atmospheres or something. Come up with your own ideas. And minute shipping of anything you want that's really small. Rich will use it.
Okay, so we chose a simulator, and as software we went with OpenRocket, which is open source and someone developed it for their PhD. Free, community driven. We actually found out that it allowed for a listener system to jump in and modify acceleration or atmospheric conditions or some specific argument. They had a really nice system already ready for it.
Unfortunately, in Java.
Unfortunately, Java, yes. And it was also already multi-processed and multi-threaded, and I spent a lot of time, which was wasted, on making it better. We also directly altered and improved the source code. They have about 48,000 lines, so we had to understand what was going on because it's not as well documented as it should be. A general timeline, we started with this little air start concept. They had a nice plugin, it was beautiful. You could start your rocket up at like 50 meters above the ground, but as soon as you put a negative velocity, the whole thing would crash and it would immediately kill the rocket because they were checking if your velocity is negative, then kill the rocket. So we had to go in, figure out where that was happening. We did visualization. We showed that before. We're going to show that again. We have TCP or TCP connection. We send over data. We simulate the rocket. We can see it in 3D. It's pretty nice to look at. Between Java on one hand and Python with Blender or the 3D, it was very painful to set up networks. We started with simple Monte Carlo for 1D. So 1D meaning Z-axis only. Rocket's not allowed to tilt at any angle or roll. It just directly goes down. Very simple. Then we added thrust vectoring, and we still don't know if it's right, but close. There's some moments. There's a lot of moments going on. Some of the air friction.
If it works with incorrect thrust vectoring, you can learn to work with correct thrust vectoring. It doesn't matter.
We got some of it going, and as we started seeing some forces being generated in the right directions, we feel that this is as close as we're going to get. Also, we resolved the 3D implementation and a lot of details, and we're going to get into that.
Yeah, so here's the coordinate system for our rocket. OpenRocket uses sort of a weird convention, which is the direction of flight is in the Z, whereas normal aircraft, the direction of flight is in the X. So regardless, Z is up along the X is rocket's length, and then X and Y are orthogonal in those directions. And then you have roll, pitch, yaw, indicated by those circles. And for our gimbaling coordinate system, we decided to go with cylindrical because it's a two-dimensional representation. And the less dimensions for us, the better. So this worked fine. And one angle is the angle from the vertical that we call Z, and then one is the angle axial that we call Y. here's sort of a Freebody diagram for the rocket. So the main things we have to consider are the gimbal thrust, and that's a function of time because as the rocket flies, it burns fuel. It gets the thrust that it can generate actually decreases or increases depending on where in the flight you are. The gimbal angles that are selected by the policy, and then the throttle percentage value that's selected by the policy. Gravity is a function of height. Aerodynamic drag, and in our case, like not really, but because it's so low. The aerodynamic drag, and gravity is pulling down, by the way, and then the in case you couldn't see it, it's this blue arrow. So this is the model. The rocket is up. The gimbaling applies at the bottom of the rocket, so that's going to apply a moment and some sort of linear Cartesian force. There's aerodynamic drag, which in this case it goes up because it's slowing the rocket down as it falls, and that's a function of the rocket's velocity, the air temperature, and the height. And then we have the aerodynamic torque, which is sort of the same thing, but it's going to cause it to rotate depending on the speed it's falling.
Or to say the rockets are meant to stay straight when they go up, not down.
So we started with a very not nicely looking Java implementation, but now this is kind of how it looks at the moment. So we have a general RL model class that triggers the step update and the terminal updates. This is general for any different method. We built this because we wanted to try out different methods. And it also generates the possible actions that can be taken. Actions that are not, actions with information that is not contained within the state space are not limited. So for example, if we don't include gimbal Z, that means that my action on gimbal Z can be from the absolute minimum to the absolute maximum. So we had to make sure that that was a valid thing. The different models just get plugged into there, and they have either a terminal or a step reward, both for stabilizing or landing. They can be different. And let's go to the next slide where I explain what happened. So we started with this large MVP, and it was really cool. So state was a function of altitude, velocity, time, angle X and angle Z. So only two angles, but we did a little special angle system. And the actions were thrust, gimbal Y, gimbal Z. And we did some discrete approximation, just take integer numbers, and it turned out to be 6.45 billion. And we don't have 6,000 gigabytes of RAM, so we can't do that. Obviously. So the issue with this traditional system was that we had this hash map, and we just index the hash map based on the state, based on an action, index the hash map, read and write. File size got over a gig. This was before we added time. Too many collisions. It was taking too long to load from the file. It was taking too long to even run simulations because there were too many collisions within the hash map. So we actually moved to a float matrix, just pure float matrix, and we had to predefine all those ranges. And so we moved to this coupled system where now the function value tables are about a megabyte each. So splitting it up into two MVPs was pretty cool because now we have a lander that works on its own, altitude, velocity, time, and chooses the thrust. And then the stabilizer, which is a 2D carpool problem, where you have angle X, angle Z, and your gimbal. And so these can work separately. There's one only cares about landing, one only cares about staying straight. And now, to be able to do that separation from before where all the data was aggregated, you have to assume that stabilizing at any altitude and or velocity is the same problem, which is a big assumption. For altitude, it's fine, but for velocity, you could have a certain amount of friction, so maybe like stabilizing when you're going really fast is easy. It's harder when you're going slow, which makes sense, but we had to make that assumption to be able to split them and make it feasible. This is a slide to introduce RL in general. People that don't know RL, so most people know RL, but so the Monte Carlo approach is you do something, you go to the end, you see what happens, and then you see where you landed or what happened at the end of all your actions where you died, and then you go backwards up and you update everywhere you were. And you say, okay, it was kind of good to be here, kind of good to be here, kind of good to be here based on where you landed. DD is an approach where you just go a couple of states out and then you calculate a little difference, say, okay, this is the change, I think this is better, and you just keep doing with a sliding window. And dynamic programming is just the approach to kind of free-for-all, optimized brute force. That's what we called it a couple years ago.
Optimized brute force.
Optimized brute force, because you just, optimal structure, so you try everything, and then you collect all your data, and then you back propagate that. Landing with Monte Carlo. So we decided to land with Monte Carlo because we felt that it was reasonable. So you just go through the whole way, do some random stuff at the start, and you back propagate. How did I perform? Monte Carlo with optimistic initial values, so everything's set to 0. You're always going to get negative rewards. So whatever you do, it's going to be worse than what you didn't do last time. Eventually, you're going to learn the whole state space, and you're going to always choose the optimal action. This is some code. So whatever was in the bottom left that we've seen in the book is here. Not that much code, but the critical, more important things is that our terminal reward is a function of landing velocity and your altitude plus 1, the negation of that. So the harder you hit the ground, the worse it is, and the higher up you die, the worse it is. But now we're always dying on the ground, so it's actually not impacting anything. But your landing velocity is what is impacting you. And then your reward at each step doesn't matter really what you're doing. We want to allow it to learn. So yeah, TD being used instead for that vertical for the stabilization, because TD you can really just, you don't have to care, oh, over the last 50 states this is my behavior. I'll just care what I did last time a little bit more. So you can always aim to stay stable throughout the whole trajectory. And this is how we saw in class. Same kind of concept, same type of code. Again, this is really, the way we set up the whole thing is pretty clean because we can use TD for either of the methods or Monte Carlo for either of the methods, and all we have to do is change 2 little functions down here. For stabilizing, in this case with TD, terminal stabilizing is set to 0 here because we're not updating a terminal. The reward stabilizing used in TD for the step update is a positive number, and it's 1 over the square of your degrees, of the degrees you're tilted at with your z-axis in the moment. So the square this is just a conversion, 180 in math up high. So if you're at 0, you're perfectly great. If you're tilted, then you're going to be penalized, and so that's 1 over your degrees.
That plus 1 should definitely be in the parentheses.
Yes, I definitely took a picture after cleaning this, and the plus 1 should be in the parentheses.
Okay, so we're going to try to do some live demonstrations, which is always dangerous. So the first one's going to be training the 1D case from scratch, which should take about 1,000 simulations. Then we'll show the 3D without a train policy, with a sort of train policy, and then we have a video of the best that we've had.
It's going to be stressful. So this is just a huge
Yeah.
source project code in Java. And again, as I was saying, we added our own listeners and extensions to the system, so the setup time that we're going to spend is going to be minimal. But I'll just ensure that we're actually running in 1D. This is OpenRocket, and you can see a bunch of simulation data on the top. But we're going to look at it, and it's going to be a lot prettier, because we're actually going to see this with our eyes. So just 1 second for setup. Wow, that's a really small window. Yeah, it's a big Java program, and you can only compress it so much. I'll run that for a minute. So let's take a look, maybe not. I think cancel is going to restart, right?
We'll retry.
Oh, retry. Okay. So yeah, we had something called the simulation type, in which we decided that for 2D you could only move one of the angles minus pi and 0, or pi and 0. So you can only do one side or the other, and then one of the angles could actually do the whole circle, so you would know which side you were with this side, but you couldn't slide in the rest of the half circle. Okay, trying this again. We automated the vast majority of this, but we still had to leave some UI stuff. We actually are considering pushing this to the community, too, by the way. Close, maybe.
Works.
Works. No.
So why?
Did you reset the model? Yeah, we have the right port. Okay.
So live demos.
Live demo is not doing great. Yeah.
Live demos are always the better.
Is it it's Windows' fault or is it the live demo? Okay. Well, we have a video though, so I promise. We wanted to train it live. That was the idea.
So why is it not
You hit reset model. I don't know. It's not even the update's not even going through. Oh well.
Maybe
Go for it. We try. Rerun. We just ran into this 2 minutes
No, it
ago.
was working 2 seconds
And then
ago.
it stopped, and now it's working, and then it didn't work anymore.
The more observation.
Oh! Okay. Do you jump into the other UI?
Yeah.
But first you want to select a couple. Okay.
Extremely.
This is extreme training. Oh. Okay.
So we've updated the visualization.
Much better now. It's on a disco floor.
So this is 1D, so we're only going to see it land slower or harder, but we are running a lot of simulations in at the same time as this one's running, So-
it's beginning to learn.
sometimes. Oh, wow, that was, that's actually really good. Some of these are really bad. There is a variation at the start. We're starting from 50 meters, plus or minus 5 of altitude, and negative 30 meters per second, plus or minus 5. Also, the angles are randomized, so there is some randomized angle start in the 3D, but as we can see, it's slowly getting better and better and better.
So let's do the 3D because we're too slow.
We're too slow?
Yeah.
You are still running SimType 1D.
I've heard it change.
You also didn't save it.
Yeah.
Oh, completely bad 3D? Okay,
Yeah,
bad
bad.
3D it is. So we're going to run 3D without any RL, just all random policy of how before the training would have looked. Hopefully Blender will not die again.
I have faith.
You have faith? I have faith. Make sure the port is set. So I have a question whether that's an issue or if it's like it has to allocate the table in something. Can you run Sim 7 first, by the way?
I think. Perhaps. Important.
Or maybe not. Well, this is not working again. Okay, well, we can't get it. But as we saw, at the start it was going down pretty fast, and now it's going down slower. Oh, we can't show 3D anymore. This is so strange. Oh, there we are.
Okay.
Okay, this is the randomized policy. So, yeah, let's go. Let's take a look at this guy. So he doesn't know anything, and he's trying to stabilize in 3D. This is at the start. Again, Monte Carlo for lander with optimistic initial values, but for stabilization it's TD. So the landers, it's going to take a long time for it to learn, about 1,000 simulations in 1D. But the oh no, yeah, but then it slowly learns some things and tries to do a couple. It's very challenging because then it takes pretty straight. It learns some stuff, but this is pretty bad. But this is what would happen at the start
Used to like
after we got the physics to work. Because we had to add thrust vectoring, which was there before. Oh, we have the video now?
Yeah. Well, yeah. Now we'll just move into video. So.
Go for it. So this is a video of our latest stuff with 3D. This is just a sub-problem in 3D where the initial angle was 0 and so it just stayed vertical. See a little bit of tilting. This is the best video to look at, and you can start seeing a lot more tilting going on, and it's able to manage to fix itself. Ooh, black frame rate. And then notice how the vertical velocity is low. We're penalizing based on vertical velocity. So what happened is it found a sub-solution because if you land like the shuttle, then your vertical velocity is very low. But that is one of the optimal solutions. So again, yeah, this is another one where it just flips over on the side. But then this is what happened last night. That was actually a 360. So
That's really
the
nice.
TD, this was Monte Carlo with TD. So it was back propagating, and it said at the end, as the video loads, at the end, if I'm upside down, I technically I'm vertical still, so it's positive, so I back propagated, so it started just all the time, just doing 360s. So that was awkward.
All right, here's some MATLAB plots of one successful flight. So you see we start at 50 meters. This is the altitude in blue, and it goes down to 0 in about 4.5 seconds. The velocity starts at negative 30 meters per second, and you see it gradually goes to about 0, and then this green down here is the vertical angle. So it started at 75 degrees, so a pretty good tilt on it, and then it kind of came back and it started oscillating around the middle. So that's what we wanted to do. We're not using angular velocity in our state definition either, so it has no sense of momentum, so it can't do better than just oscillate around the center. And then here's the policy learning. So the original hit was at negative 10 meters per second, and I don't know why it gets worse at the beginning, but as we go up to 1,000 episodes for the 1D case, you can see that our average, goes up and winds up making it to, basically 0.
With some at the end still being really bad.
Yeah, and
Outliers.
something that is important
So you don't
is
put people in these rockets.
our dimensionality, our state approximation is the precision for altitude and velocity is 1 meter.
Yeah, that's a
So,
good point too.
Getting less than 1 meter is very hard. And again, that's only 1 meter precision, so yeah, that can be a problem. And we do not allow duals to be in the same state. Once you're in one state, you can't get in the same state again in that same episode. We actually had a huge bug in our code where we would be in a state, and it would simulate 20 milliseconds ahead, and we'd be in the same state, and it would take a different action, and it would be in the same state and take different action. So we fixed that.
Okay, so it's not too much future work. Is change. Increase the simulated motor accuracy. Right now we kind of have some hand waving about how it kind of turns off and thresholds, so that can be made better. You could do full flight, so go up where it has to conserve fuel and everything, then fall back down and control itself. Increase the learning rate and the consistency, which is I think just an obvious given, and then to colonize everything. I think that's it.
Okay, any questions?
So there's the mesh size for simulator. There's the mesh size for.
You said for the simulator?
Or is it continuous? Is the simulator doing stuff?
Yeah, the simulator is you can set doubles. So it's
You can set the simulation step time to like 1 millisecond. No.
No,
Yes.
I think it's like 4 milliseconds, 5 milliseconds.
But I think I see what you're getting at. It is getting the real values, while the state would stay at 1 meter. The state would be at 5 meters, and then it would be at 4, and then it would be, but yeah, so as long as it's within the box, the state stays the same, but the simulator is showing what really happens.
Simulator is really accurate. It even takes in the Coriolis effect for some reason.
Yeah, which is one of those courses that you never see.
Yeah, you're at for a lot of the time.
You guys should do a
Log normal.
But no.
I mean, it fixes that thing where you have like 1 meter.
Yeah, you had suggested that we use log for distribution. We didn't get to that. We recently made the jump of doing a float matrix and splitting it up into the coupled system. It felt like really dangerous to say, yeah, we can just assume that stabilizing is the same always at any altitude, but it works. So
And then have you guys been able to do the gimbaling on its own? So separating without, just letting it free fall for 100 miles or something.
well, if you let it free fall, where's your gimbal?
It runs out of fuel though, too, so we didn't just have it train Infinite Horizon or something. We trained it while it was fall. So no, it was weird. I mean, we did TD for the stabilizing, so.
There's potential potential. We were going to try Sarsa, but then we didn't get to Sarsa, and then there were a bunch of bugs. Oh, do people know what happens? This is a trick. Okay, you have a circle. Okay, there's an angle, right? Let's hit right here. This is obviously 0. This is pi over 2. This is minus pi over 2. If you want something to be defined in 0 to 2 pi, what happens if you mod by 2 pi? What's your opinion? What's negative pi halves mod 2 pi?
Negative pi half plus pi.
Wait, what? So
Are you
negative. So minus 90 degrees.
I think he got you.
what's your? That is funny.
I think his answer is 3 pi over 2.
3 pi over
I
2.
think his answer is not negative pi over 2.
It's not 3 pi over 2. For some reason, it's flipping this.
But is it Python or Java?
This is Java. So easier example: 3 mod 2. We all know it's 1, but negative 3 mod 2 is 1 again. So what's happening is it symmetrically flips whatever's down here up here.
Yeah, so what is
So why was this a problem?
negative pi half?
Minus 90 degrees.
What is it modulo
3 halves
of
pi. Oh, what?
What is it modulo of pi?
I'm pretty sure it's pi halves. Right? It's the same as 3 mod 2. It's an implementation detail. They don't conserve the sign, and that gets lost. And so what was happening is it was considering this negative 30 the same as plus 30. So the rocket didn't know what it was doing. We were doing that over
And
rapidly.
that was both for if the rocket's tilting, like whatever radial angle it's at, it was symmetric about some point, and then the gimbal was also. So,
we found that out Monday night, I think. Very unfortunate.
Good. Any more questions?
So there's this 4D way of robotics. They call it quaternion.
Quaternion.
Yeah, you should have used that instead of normal.
So we only used 2 dimensions to define the rocket's orientation because we cheated and said it couldn't roll. The quaternion is 4-dimensional, and
Yeah.
you saw how big it was already, so we couldn't afford it.
They use
I wanted to use
underlying-
more. Yeah, I was like, let's use the whole rotation
Their
matrix.
underlying system uses them. But they also give us a handy converter to stop using them.
Yeah, we had to do a lot of that
But
math.
because we don't allow the rocket to roll, which, by the way, if an actual rocket starts rolling and it only has a gimbal to slow itself down, it can't slow itself down. You just have to wait for the air friction. And actually, OpenRocket considers no radial air friction, so it just keeps going if it starts rolling. So we just said, let's just say it won't ever roll. That's
So
one of our
roll is
assumptions.
this one. There's also special names for each axis around the
We
rotation.
introduced that.
We covered all those angles. You're right. They're all the different rotations, so that's been a challenge.
We wasted like hours probably trying to figure out how Rocket simulated, what is it called, OpenRocket, did all that versus how we interpreted it. Like, so much time was wasted.